want to walk you through, I think it's maybe 4 or 5 of the tricky problems at the end of chapter 23, Sapling Homework Part 2. These are all multi-step synthesis problems, and they just, they're a combination of reactions that we had at the end of 242, and then reactions from chapter 23, and some of them are really, really clever. And so I'm just going to go through them. So in the first one, we're trying to add both a halogen, or 2 different halogens to the ring, and we know that we can't do it with our traditional electrophilic aromatic substitution. Like say maybe put the bromine on first and then follow that up with the chlorine in the normal way that we would do that, because the halogens are orthopara directors. So if we tried using electrophilic aromatic substitution, we would end up with ortho of the product, or we would end up with para, but it definitely wouldn't be right. So we can't use the methods that we already know. If you're looking at the problem right now and you're looking at the possible things that you can start with that will add functionality to an aromatic ring, you do have the Br2 FeBr3 reagent, so you do have the possibility of starting by brominating like that. Or the other option that you have is to start by putting a nitro group on the ring, NO2, because you have nitric sulfuric acid. If you start by brominating, then you're going to be setting it up to place the next substituent in either the ortho or para position. And like I said, that's not the right spot. That is not where how we're trying to arrange the substituents on this ring. So that means that our first step is going to be adding the nitro group using the nitric sulfuric acid HNO3 with H2SO4. Even though that's not the substituent that we actually want on the ring, it is going to make the next substituent go into the meta position. So this is what we want to do. Now the next thing that we want to put into the meta position, we want to put either the chlorine or the bromine. It really doesn't matter which one. However, we only have the reagents for doing the standard electrophilic aromatic substitution bromination. We don't have Cl2AlCO3, so this has to be our second step. And then that means the end of this reaction will be to convert the nitro group to the chlorine. So you can do a reduction reaction on a nitro group to convert it to aniline, and there is quite a few different reagents that will do this. I think the reagents that you're used to seeing are zinc and HCl, if I remember correctly. And in this problem, it's giving you the option of iron with HCl, which is going to do the same thing, or it gives you the option to do hydrogenation. And then once you get that done, it's 2 steps, which are reactions that you learned in chapter 23, to get you from the aniline to the benzodiazonium or aryl diazonium, and then convert it to your final product. So you should be able to take it from there. For the next one, question 11, this one is really similar. It's not quite as complicated because the 2 substituents that we have on the ring, they are both meta-directors. So we can a little bit use the standard reactions that we learned in 242. We don't have a way of putting a nitrile CN group directly on the ring, so that means that we're going to have to start by putting the carboxylic acid group on the ring. Oh, actually, we don't have a way to put a carboxylic acid group directly on the ring either. So both of those are multi-step processes, and you should start by putting the carboxylic acid group on the ring first, because it is not as strong of a deactivator as the nitrile cyanide group. So that should be the first thing that you put on there. And this is going to be a 2-step process, which you learned in 242. So your first step is going to be to put any alkyl group at all that you want on that ring. And you've only got one option. And then you're going to do the side chain oxidation reaction, which is KMNO4. and that's going to give you a carboxylic acid. Once you get the carboxylic acid on there and you're ready to put the nitrile group on, that's going to be a multi-step process again, because you're needing to do this through the aryl diazonium. So your first step is just going to be to get that nitro group on the ring, and then your next step is going to be to convert that nitro group to the diazonium group. And nope, that's not right. Your next step is to convert it to aniline, NH2, then convert it to the diazonium, and then you can convert it to the nitrile. So you kind of get the pattern with that. That's not too tricky. Or actually, it is really tricky. Question number 12 is coupling is one of those azo coupling reactions. And the problem doesn't look like this. When you look at 12, this is not what you're going to see. Because it's describing this reaction in words. It's saying that you have a slurry, which just means a mushy mixture of aniline and potassium nitrite and hydrochloric acid, and then you're adding 4-ethylphenol, which is this guy here, and it gives you 4 choices of possible products that you want to select. So this reaction, our aniline is going to be converted to the diazonium. Actually, probably more useful to draw that group out. Converted to the diazonium, and then it's going to couple itself to the benzene ring of our phenol molecule. And so knowing that, when you get that far along, that's going to narrow your possible answers down to 2, because 2 of the possible answers do not have this correct functional group in place. And then the next part that you have to figure out is where are the OH and ethyl substituents located on this ring. Now, obviously, they are going to be para to each other. So you're going to be looking at possibilities like maybe it looks like this, or maybe it looks like this. And this was not something that I talked about in the notes, but use your organic chemistry intuition. Think about steric hindrance. Think about what you know about molecules, big molecules coming together, and choose the product that makes the most sense based on your understanding of sterics. Now, this last question is a doozy. This thing really had me stumped for a while. It is quite fantastic. It's a 5-step reaction, and it's giving you a lot of options for the reagents for steps 1 through 5 that you have to figure out what you need to use. Now, clearly it's going to be a aryl diazonium reaction, because that's what's going on in chapter 23. And so the first thing that I did, just knowing that I was going to need to use that particular synthetic route, the first thing that I did was put the nitro group on the ring, and then I reduced the nitro group to an aniline. And Sapling, just to try to keep you on your toes, it's using a whole nother set of reagents for this reduction. But you should, just by reasoning, you should be able to find reagents similar to what we use, which are zinc hydrochloric acid. You'll find something similar to that, and you'll get it reduced down to the aniline. And then the next thing that it wants, so we're not all the way there yet, because we have 2, let's see, this is step 1, this is step 2, so this will be step 3, and this will be step 4, and then this will be step 5. So we still have we have 3 more steps to go. So when I got to this part, I was pretty stumped about what I should do next. If I convert at this point, if I convert to a diazonium, then I could maybe do some, because this would be a meta director, I could be able to put some stuff out here. But the reagents that you have to choose from don't make sense for that type of pathway. So I was pretty confused for a while, until I realized that this guy, because it has a lone pair of electrons on the nitrogen, This guy is an orthopara director. So with that aniline, with that NH2 group on the ring, you can put all of your, I'm repeating a step. You can put all the bromines with the aniline group on the ring, because it's an orthopara director, you can put all the bromines on the ring exactly where you want them to be. So when I was first approaching this problem, I was trying to approach it in the way of like making an aryl diazonium and replacing that N2 group with a bromine. But I realized that actually I maybe want to use the aniline group as a way of directing all of those bromines to the right spot. And then, and this is where I'm going to leave this up to you, in the next two steps, figure out how to get rid of the NH2 group. So it goes away and you have the molecule that you're looking for.